has his basis at the Symmetry Conference in the year 1989.
Yes, then it was formed, yes.
Well, he has the two-way award of the International Association of Shell and Special Structures for his paper about chiral Polyhedra. And he will speak about the roundness of Polyhedra.
Thank you,
please.
Mr. Chairman. Well, good morning. Here you see just a number of models of a few what I call the family, members of the family of Polyhedra, or polyhedroids, so to say. You maybe recognize many of the irregular ones, the semi-irregular ones as well. Just a moment. Here are a number of semi-irregulars. I will concentrate on this. Prisms here, anti-prisms, but also dome structures. They all belong to that group of polyhedral structures, so to say, polyhedral forms. Well, I will concentrate today on the roundness of these polyhedra. Roundness can sometimes be a very important aspect, and that is why we have to try to find a proper or suitable definition of what we mean with roundness. Well, first of all, I think that all faces should touch the same inscribed sphere. That's one of the main aspects. All corners lie on one circumscribed sphere. This is what all regular and semi-regular polyhedra have in common. As a whole, the solid is convex. It's also the same with the uniform polyhedra. The radius of the inscribed sphere should be closest to that of the circumscribed sphere. The difference should be as small as possible. It also should have the smallest deficient angle. I will come back to that later, in order to make it more round. And then it has the largest average dihedral angle. The shallower the meeting is, the rounder its shape is. Generally spoken, of course. Well, these are the well-known Platonic and Archimedean polyhedra. You may notice that there are, in fact, sometimes they say there are 13 Archimedean solids, but in fact there are 15, as this one, number 15, and left and right are what we call chiral ones, the left-handed and right-handed version. The same with the number 8, sorry. The same with number 18. Well, I've numbered these just for practical reasons, as you may have noticed, after the number of faces, number of vertices, and the radius of the circumscribed sphere. This gives an order of sequence that gave me the inspiration to call them like that, from P1 till P18. And this is what shows what I mean with deficient angle. This is part of a truncated icosahedron. You know that it consists of 20 hexagons and 12 pentagons. When you put these together in one corner, these three of these meeting polygons on one flat plane, you see that there's a part of the material has to be cut out in order to be able to fold it so that it becomes round. All Platonic and Archimedean polyhedra are composed of any of these polygons with 3 to 10 sides. But you see that each of these has a different circumcircle, and this means that when you put these on the same sphere, the triangle is farther away from the center than the pentagon, for instance. There's a great difference can be there, and that is what we try to find a solution for. So larger polygons have larger circumscribed circles and are therefore closer to the center of the circumscribed sphere than polygons with less size. And polyhedra consisting, that's also important, consisting of polygons with different numbers of sides, have more than one inscribed sphere. That's these polygons. Roundness can be important for dice, for instance, particularly if they are used for poker or backgammon. You may understand that great economic values are in stake then. Sports balls, and especially soccer balls, that is a subject that I have specialized in, and dome structures also. Well, you are familiar with that. Well, polyhedra used as dice must be perfectly isohedral, as I said. Isohedral means that all faces have the same distance from the center. This is correct for instance, the die, the one on top, the most usually commonly used dice, which is based on the cube. But all Platonic solids have the same characteristic, that they have all their faces at the same distance from the center. There's one problem, when you use this as die, they all must roll very easily on a flat surface, but on the other hand, they must have always one flat face pointing upwards if it is come to rest, when it comes to rest. You see the one over there, the tetrahedron, is not very useful for that purpose. There are two others that almost are not Platonic. Those two are in fact what I call compressed forms of dual antiprisms. I will come back to that later on.
Do they,
sorry?
Dice, do they take into account the fact that there's usually a hole and therefore there would be a slight weight distribution?
Sometimes they do that trick, yes, and they even, oh, you mean the slight hole in the top, you know?
Well,
they have to be filled up with the same material again. Because otherwise you have that problem that you say that they have a preference. And that should not be the case, of course. But sometimes they do tricks in it, drill holes in it and put metal in it so that it has a preferential side, you know. But it is, of course, not allowed. Well, this is quite a great review of all the data of the most important data of the Archimedean polyhedra. But what I think is an important aspect is number 17, for instance, has the smallest deficient angle, as you can see. Others have larger angles, so this is a quite interesting figure. And also the radii Ri is the inscribed rays of the inscribed sphere. 1 and 2, they have 2 or even sometimes 3 inscribed spheres, but in this case they are very close to one another, and this is sometimes very different when you see it. Look at this one, or most of the other ones have quite some difference, but the number 17 is comes out a little bit better. Then the next aspect that I want to talk of is the principle of reciprocity, or the duality of figures. You see this demonstrated here for what I call P11, which is the rhombi, well, you know, the one composed of squares, hexagons, and octagons. P11 I have called it, and R11 is the reciprocal figure, as I call it. And here you see them all together, the polyhedra themselves and the reciprocals. And you may notice that the top row, the regular ones, are reciprocal to any one of the other reciprocals. So the icosahedron, for instance, has a dual which is a dodecahedron, and vice versa with this one, cube and octahedron also, and two tetrahedra are dual to each other. But the others have quite complex figures, as you may see. And these are them, in fact, when you see them on themselves. But you see also, may you notice that there is a certain kind of roundness which becomes larger when you have more when the model has more faces. Well, here again, you see what I in the beginning said, number 17 has the largest dihedral angle, xi, this dihedral angle of all. Which also is one of the aspects that is important in relation to roundness, as I said before. And there is one other, the rhombic dodecahedron, number 12, is interesting because it has a dihedral angle which is 144 degrees exactly. This is the one that we all know as the honeybee comb. Well, then I come to the prisms. They have in fact the same characteristics as all other polyhedra, composed of regular and similar or regular polygons, convex, and all corners of one circumscribed sphere. So they are interesting in this context as well. These are the duals of these prisms and antiprisms, but these duals have very large difference in circumscribed spheres. You see, the horizontal ones are much smaller than the vertical ones in many cases. That's why why I showed here what it looks like if you compress it in vertical direction. It keeps most of the characteristics of the top one, but now it is better if used for dice, for instance. I guess that the number 5 or number 6 was shown on one of the previous pictures, where I said that this is often used for as a dice. Well, it is interesting to see that the polyhedra can be sorted following the number of faces, and this means, in fact, that members of each group can be made isodistant, as I call it. They are generally called isohedra, as they have all their faces at the same distance from the center. You see, number 12, 13, and 14, for instance, there are 3 different ones that all have one isohedron as their one which has the same number of faces. Well, this is what I will discuss next. You see, these are the Platonic polyhedra. These are isodistant, in fact, in themselves. They all have the same distance from the center because they consist only of one type of polygon. But there is another one, number 6. This is the truncated tetrahedron. If you convert this, it becomes a octahedron again. So this one, what I do in the next is call them after the number of sides. When I talk of a 8-hedron, I mean, in fact, the isodistant octahedron. This is now has no real sense now, but when you look, for instance, at this one, the 14-hedron, it consists of 7, 8, and 9. The numbers 7, 8, and 9 have this one in common, and it is found this way. You see, all 14-hedra are truncations of the octahedron, in fact, and when you do it in a proper way, I cut an extra part from it so that the brown face, or what is brown faces, become at the same distance as the blue faces, and this leads to a new figure having irregular hexagons and larger squares as these faces. I call this the Fortinhedron, and you see that they all fit on the same circle, which is important, and this has to do with the fact that they must fit on one circumscribed sphere. But it is also interesting to see that the ratio of the sides, A and B, is based on a quite simple equation. They are relating sinus 45 to sinus 15. The 26 hadron is this one, the one, in fact I have a model of that. This is the 26 hadron. You see rectangles, and this is actually a small an octagon with chamfered ends, and triangle chamfered in the same way. And well, this is again, and the 26 hadron is derived from one of these two, 10 and 11. This is the rhombic-cuboctahedron, and you come to that one. That's the model over there. The 26 hadron is found. By truncation of this, and you get that one, yes. And then starting from the 32 hadron, which is in fact this one. This is the truncated icosahedron, but this has different distances from the center, the pentagon and the hexagon. But you can make it such that they will have the same distance, but you see that the hexagon has other side dimensions. But this forms the basis of three different polyhedra. You see it is done like this. First of all, this is the truncation itself. And this is the end. This is the what I call the 32 hadron that you find. This is the 32 hadron, where an extra piece of material has been cut off, and you again find a very simple relation of the sides A and B, as you may see, sinus 36 over sinus 24. This is the second truncation of the icosahedron, truncated icosahedron. The 62 hadron is found from 16 or 17. You see it's demonstrated here. It starts from the truncation of this one. You can, this is the iso-distant form of this one. When you start from this, you can cut off parts again, as I show here. And then you find that other one. This one, I have a model of that. In fact, this is the one that I show here. You see that it is again built of rectangles and pentagons and triangles, but they are not really triangles, but they have chamfered corners. This is the layout. You see, well, it is very clear that you have these deficient angles, and they all fit again on the same circle. You see that there are now three different side lengths, let's say, but they still relate in very simple numbers, integer numbers. Well, the 38 hadron is the more difficult. That is the one over there. Well, I thought I had a model of that now. I haven't got that, but I'll come to it later. But you see, the problem is there. You have to find it by starting from the 14-hedron, which was shown over there. This is the 14-hedron, and then which has all its sides at the same distance, and then put a triangle and a square on top of it and rotate it so that all corners stay on the same edges, but as is shown there, this can be rotated, but the corner should stay on the other edges. And in the end, points 2 and 3 are connected to form that face 1, 2, 3. And this can be found, as we know, that the ratio of the sides must be like this. We can find that from the circle, the circumscribed circle. That is. And by iteration, one can find that the rotation angle must be like that in order to make this equation true. The 92-hedron is again a much more difficult case. Well, this is the 92-hedron. You recognize this, of course, as the snap dodecahedron. But in this case, all faces have the same distance from the center. But it is not, they are no longer regular triangles, but slightly different. And well, this is done the same way. But you see, what you must know is that all faces must fit on one circle, which is shown on the left-hand side of the picture. And when you take out that particular triangle, 1, 2, 3, the angles can be derived from this figure, being 36, 84, 60, and the ratio of the sides follows these numbers. So the rotation angle again can be found the same way as we did it with the truncated cube. No, not the truncated cube, but the oh, sorry, I forgot the name, but you know what I mean. But this one is placed on top of, or is derived from this one. This is the isodistant 32-hedron. And you see what we do. We do it the same way, but we know that the ratio of the sides must be sin 36, 84, 60. And as well, this is again found by iteration. You see that corner is 3.3, etc. And that gives the proper dimensions. Well, to build such a model, always 4 triangles can be combined to form 20 larger triangles, as is done here. And well, I will come back to that later. You see here, these are all the different semi-regular faces of semi-regular isohedra that I've spoken of before. And they all fit, you see, all faces fit on one circle. This is one of the main conditions. And in the end, you can see that starting from the regular polyhedra, they have, of course, have no parent, no counterpart, but the others have. This one, the number 6, has, as I said, the 8-hedron or octahedron as its counterpart, and the others are related to that. You see, sometimes 3, sometimes 2 form just one isohedron by cutting off parts. Well, I applied this system, this idea, in soccer balls. I try to, at least. Well, what you see here is a picture of the 26 ball. This is the 26 ball, what I call it, which is based on this form. you see that it has roughly has triangles, rectangles and squares. Well, maybe you want to look.
You can buy this, can you?
This one is not in production. The other one is.
It's not in production.
This one is not, because, well, there was no interest in doing that. The next one is the 96 ball. This has been tried out in the beginning by Adidas, but they refrained from it because they thought it was too difficult to make. This is the 92 ball. You may notice that it is composed of large triangles and pentagons. But the large triangles consist actually of four small triangles. And what in fact, what I think is the most promising one is this one. Is what I call the 62 ball. Well, this is based on this isohedron.
It's in production, is it?
This is in production, yes. What I will explain. Well, this is the construction of that ball that I just gave, the distance snap dodecahedron. Here again.
Advisor to these?
Sorry?
Are you an advisor to these companies?
Well, not, well, in fact, I had a patent on it, and I sold the license to one particular firm in Pakistan, and they are producing this.
Do you have to share with Archimedes?
Maybe. Well, this is this is the rhombic dodecahedron, that one of the 62 hedron. This is what it looks like if you inflate it. But the point is that it consists of 62 parts, which means that the seams are very long, you know, much longer than in the standard ball. And well, I have thought of a solution for that, and think I have found it. You see, some of the rectangles can be subdivided to some extent. You see, it can be formed from two small triangles, the red ones, and two trapezoids. And these trapezoids, for instance, can be added to these two white trapezoids added to the triangles. Well, triangle, actually it is a hexagon, so you may notice. And the red parts are added to the pentagon, or decagon actually. And you see, this is what it will look like in that case. But these parts, these four parts, can of course be made in one piece. They are punched from one piece of material, but and they have to be folded a little bit. I will demonstrate it on the model, and in the end it looks like this, where the seams are along these sides, and they are again have the same length as in the original buckyball, as they call it. I think by mistake, isn't it? You are. Well, this is the way it is composed. So you see roughly hexagons and pentagons again. Again, 12 pentagons, between asterisks, and 20 hexagons. This is in inflated shape. Well, there is an interesting to compare these two, the original standard ball and what I've called hyperball. Just a name. The area difference between hexagon and pentagon is, in this case of the standard ball, 51%. The hexagon is 1.5 times larger than the pentagon. And in the other case, the difference is only 5%. So I think this is a great improvement. and also the difference of the circumference in millimeter. You see the circumference of the polygons themselves, the parts, the panels, so they say, is in the first case 44 millimeters, in the other case less than 4 millimeters. And well, I thought that these might be interesting for application. You see, this is what is the main difference. I've got a model of this as well. You see, you can make inscribed circles on the panels, and you may notice that the hexagon has, for this particular size of ball, a diameter of 77 millimeters, and the pentagon only 61. There's a 25% difference or so. But in the case of the other one, you can, when you the new ball, so to say, when you write on this ball the circles, you can print on these balls 32 touching circles with a diameter all with the same diameter, 70 millimeters, which means that in this case the span of the panels is equal for all panels. And in this case, the span will probably is great, and it means that it has a quite difference in stress distribution, maybe when you pump it up, and well, what I say is, so I have explained this already. So the hexagons are 51% larger than the pentagons, and in the new ball, the hexagons and the pentagons are almost equal, 5% difference. Well, this is a model where you see it was made in the same way that the panels are punched. They are punched, cutting the edges, and also punching holes in it. These are the holes that are made. This is a model of it. I'll not send it now. I can give it to you, but we may be careful because it is vulnerable. But you see, when you compare this with the standard ball, you may notice that it is much rounder than the other one. Speaking of roundness, you hear it just in one glass, and it is the point also is that the corners, the vertices, are slightly pyramidal in this case. And in this case, they are completely flat because they meet on that flat plane. The flat part of this form. Well, this is in fact the only ball where you can print in a printing pattern like this. Well, if you are interested, I could send it around. In the meantime, it is FIFA approved, so it may be used for any important match, World Games or whatever. But it hasn't been done so far. But they still must discover its special qualities. But you see what happens when you are heading a ball which is shot over a very long distance. The deformations can be quite large, and it also means that the standard ball is often found to be quite hard. And in this case, what you can ask, which should it have? The skull or the player of the ball? Any of these? When I cut, maybe both of them. Both will a little bit. But you can think, you may not, you are with me that it is important that you have a ball that is as soft as possible. But you see that all corners here are completely flat, 360 degrees. Well, I've made a few conclusions, but it more or less looks like as if I have to sell these balls, but I don't have to. But all the basic parts are a little bit farther away from the center than in the original case, but they also have difference in distance. As you may notice, at right This is the standard, right? You see the standard ball, 103 to 100 millimeter, and the faces of the other ball are closer to the sphere, 5.8 millimeter instead of 8.4 millimeter average for the standard ball. You can say, you may think it is not very much, but seeing in the whole, it is maybe 31% better in that case. Just considering it in the roundness. The corners are flat, and as I said, and the parts are almost equal. They have the same inscribed and circumscribed circles, and parts almost have the same circumference as well. And the seams also follow the sphere. You know, when you see the seams are like this. They have already a form which is closer to the sphere than in that case where they are completely straight, but here they are broken, in fact, broken geometry. Well, the next one is dome structure that I wanted a little bit to talk about. Well, Fuller, of course, is the spiritual father of geodesic dome structures. This is front page of Time, 1964, you may notice. But there are several methods of subdivision. Clinton discerns these two main kinds of difference. You know, you can find a triangular subdivision by subdividing the original edges and then find the new cutting points in the plane itself. But you can do it the other way around, the other way also, subdividing the arc and projecting these backwards to the original edge and then connecting the cutting points. Then in fact you find windows in the middle. But then the new subdivision method is that the centers of these windows are connected again. Well, these two methods are mainly used, but there are many other possibilities as well. What we ourselves did was we developed a method to produce sketches, even three-dimensional sketches of polyhedra. And we did it like this. You know, when you take, for instance, this one, this consisting of squares, hexagons, and decagons. First of all squares have to be placed in space by starting with just a square and rotating it to and copying it to various places in space. Same can be done with the others, and we have ourselves discerned. I published something about this previously, but it goes too far to treat it now in detail. But this one consists of three different rotation cases, but in the end we find the data in 3D, which means that you can build a structure and rotate it any way you want. This shows shortly the formation of an octahedron. It starts with a triangle which is put in the center of the system. Then it is placed at a distance from the center and eventually rotated. Then you see that you can put these four to form the bottom part, and then the next part is that you make the top part. So you can make any pattern, in fact, and project it onto the sphere. This, for instance, shows how this is done. You see a subdivided triangle placed in space, and then project. In this case, this is what I call a subdivision of the edges, method 1 in the previous figure. And this is what it looks like if you project it upon the sphere. Well, this is what you get when you do the same trick with the octahedron. And this is what it looks like when you make it three-dimensional and spherical, you know. And even when you start from such a small sphere, you can again rotate it following the conventions that we developed. This is the first one, top one is rotated following the vertices of the tetrahedron, the other of the cube, the octahedron. You see dodecahedron and icosahedron gives these little figures, and you can even go further. You see, this is the C60 molecule, sorry, discovered in 1985. Am I right? By Kroto and Smalley, Mr. Kroto. Am I right in that? I thought. But you see, this is rotated with using two different rotation cases, pentagons and hexagons, but place spheres in these corners and then rotated them in space. What you can do for the further subdivision of these spheres is subdivide the original polygons. These are the ones that occur in a normal polyhedron, and then subdivide these again. There are other routines which are shown on the bottom, and then you see a number of subdivision methods can be developed this way. These are flat surfaces, but subdivided following one of these methods. And then you can rotate these to form polyhedra. And then the next step is that the Cartesian coordinates can be converted to form polar coordinates. And when you make all polar radii equal to, say, a unit edge length, you get a spherical form. And this is shown on the bottom, where you see that originally you have that square subdivided in little squares, and when you project it upon a sphere, you find that the one at the right hand. But doing this with any of these are the regular polyhedra, you can take any pattern and project this upon the sphere. And these are just a few possibilities of how this can be done. But here you see that it's done for most of the semi-regular ones, and you can get very complex subdivision patterns. In fact, it is not. I don't know which one is interesting for practical application or not, but certainly take, for instance, number 18 can be one of these. It can also be done for the rhombic duals. These are particularly number 12 is the triacontohedron, rhombic triacontohedron, which is very often used for subdivision patterns. It can also be done for prisms and antiprisms. This is what we found. An interesting game that I did was trying to translate or to make Escher figures based on this principle. You see, this is one triangle part which I derived from a publication by Doris Schatzschneider, which may be well known to you. You can take one triangular part out of it and trace 1/3 of it. When you rotate it around that circle, and 3 times over 120 degrees, you get a complete figure. This is what it looks like in the end, and with colors in it. Well, but this is what I call the transformation of an Escher triangle. Well, put these together. When you put these together, you see this is layout of the net of the tetrahedron actually, and you see this all figures fit very well together. And then there's a tetrahedron, and you can do the same thing with the octahedron, 8 triangles, all the same. And even the icosahedron. But when you look at it closely, you see that the figures, the pattern is just going through all these planes. So this is the icosahedron. And this is a model of the triangle, a model of this one that I calculated with the help of our program. And this is what Schatzschneider did. You see, there's quite reminiscence, much great reminiscence. But the funny thing here is that as long as I have these coordinates, I can go on further, following one of the principles that I showed before. Well, this is a tetrahedron, octahedron, and the icosahedron. You go see the pattern is going all along the figure. And you can even explode it, I would say, convert these to a sphere. And well, and the pattern goes on. This is the tetrahedron, of course, is quite distorted, but the octahedron, the icosahedron are give a quite good impression. In fact, Escher himself also made some spherical sculptures. Maybe you have seen this on Sunday in the museum in The Hague. I made these pictures there. Well, the next step is, and I think maybe that you are interested, the sphere can be modified. It is generally described by an ellipsoid, generally described by two equations. These are the one on this page, where E1 and E2 may be different or equal. These are the extensions, so to say, the length of the axis. Sinus and cosinus of phi play a role in it, but n, the exponent of the equation, also is important, because we can make this the first equation more general when we add another one, the second equation, where another extension and or exponent is used, and then putting these two together you get an ellipsoid with a very irregular shape sometimes. But this is what happens if you change the exponent here. You see, normally this is a normal ellipse with the exponent of 2, but when you make an exponent of 1, it becomes straight. Making it smaller than 1, it becomes hollow, and even very hollow. And making it larger than 1, you get this. Well, Pieter discovered this, I think. That's the super ellipse. This is large, and even if you make it 100, in this case, it's almost rectangular, you know. And you can do very funny tricks with this. Sorry. Very funny tricks with this. You see, what I did in this matrix is changing the exponent of the ellipsoid, I should say, in one direction and in the other direction as well, and combine these in any possible combination. And you see what odd figures one may find. But even very regular ones, take for instance BF, which is in fact an octahedron, and DH, this one is almost a cube, this also is, and well, in fact this is the regular ellipsoid, and in fact any of these represents a whole group. So this is an endless number of different variations that you can find this way. Well, what I did is making a very low exponent sphere with the exponent 0.2, 0.3, a frequency of 2, and 4 sector numbers. Sectors are the numbers. The numbers of the faces in one direction. This is an octagonal one, and you can put these together in a matrix, and you can get this interesting figure. This one, I always think that the last one reminisces one of the figures that Escher made, much more complicated and much more beautiful, of course, but it is a matrix, a cubical arrangement. These are some extreme forms, a very small and horizontal, flat, very flat one, just by changing the exponents. Another aspect that is interesting in this respect is how can the world globe map be made so that it gives a proper picture of the dimensions of the countries that are on it. So you see, this is first step, of course, is that it must be digitalized, the country, the contours of the countries, for instance, and but the first projection actually was the cylindrical projection, and this is normal, but it means that all vertical lines are equally spaced, and horizontal lines as well. So what you get a very distorted picture of the Earth in this case, and there are many other possible mapping patterns as well, but this is the one that I took as an example. But it can be done better. Buckminster Fuller, for instance, called this the Damexian world map, where it was projected upon the side of the cuboctahedron, which was also called Damexian by him. It gives a better idea when you walk from instance from here to there over the sidelines. It gives a better impression of the length of that distance. But it could have been done better. He did actually, but I don't have a picture of that with the icosahedron. He did the same thing. But this is a patent from a French inventor. He projected the world map on the ISO distant 32 on this one. And this is much better, of course, because there are 32 parts now. And when you all parts have the same distance from the center, so the projections are all very well comparable, you know, with each other. And this is, well, I put a net on top of it, but this is the patent itself. And you see when you draw a line, for instance, from left to right, the blue one, it can almost serve as a measuring of the proper distance between the 2 points, as long as you pass cutting adjacent points. You must always have this one. If this one is a neighbor to that one, that one, that one, then when you connect it, you go along the sides of that are all. You can just put it in such that this gives a quite good impression of the proper distance. Well, I thought it was an interesting example of such a such an application. But you can imagine that, well, the thinker of Rodin got a bit puzzled about form of the world. Is it spherical? Is it not? As a matter of fact, it is any of these, as long as you vary the exponents. You know, by varying the exponents, it is. Well, in fact, you said that my time is up. In fact, the circle is round now. We went from the polyhedron to the sphere, and from the sphere to the polyhedron again. And well, I hope that you have got an impression of that. This afternoon, I will do a workshop in the other building at the West on the building of Kyla polyhedron. I hope that you will join me in trying to build these models about this large. Maybe that you think it is interesting. Well, thank you very much for it.
There was a complaint about at the last World Cup by the goalkeepers that they couldn't, there was something of a problem with the flight of the ball when it was hit from a long distance. And this reminded me of the problem in the golf ball, that the smooth golf ball is erratic because of the change from sort of laminar flow around the ball. So the rounder the ball is, the more problems they're likely to have, unless there's some roughness on the ball, so that the laminar flow is, starts earlier or something like this. And I can imagine a very smooth ball is actually very different. At some point there'll be a breakage and it will appear rather erratic in its flight. Is that something that's being discussed?
Of course, yeah. Well, they have firms to come with this idea. But the first part, what I think that during the World Cup, the problem was that the ball was wobbly. It was not following a straight line.
Yes.
And I think that had to do with the distribution of the material in the ball itself. Particularly the Adidas one I have a theory about what happened with this.
You don't have an example of that ball here yet?
No, I haven't got it, no. But in fact, what they do is they make they take a dodecahedron as a inner frame. What do they call that? No, you call it. They make a dodecahedron out of parts of fabric, strong fabric, and they sew it together, and then put a ball inside it, the bladder inside it, pump it up, then you have a more or less round form. Then it is dipped into or covered with a plastic material, partly fluid material, and then they put on the different parts. And the next step is that they put it into a hollow mold, heat it, and wait until it is all glued together, and then they lose it again. So it is, the outside is perfectly round. No discussion about that. It has to, you know. But the inside is questionable, because you don't ever know where the material goes as long as you heat it and
so it's pretty complicated on the inside.
Yeah, well, because they start with a very irregular shape, actually, not a very good shape. The dodecahedron has about, when you look at the model of the dodecahedron, I haven't got it with me, but the center of the sides are 27 millimeters from the outside. And by pumping it, you have to do something, you know. The material has to come from somewhere. And so I think it is quite a crimpled one, is the proper word for it. It will not be very smooth.
As it's rotating, there'll be some well, gravity shift.
Yeah, I think that has to do with this. But I think it is important to try to distribute the materials as evenly as possible on the circumference of the material. That is one main item, I think. That is even better with the original truncated icosahedron, but a little bit better with the other one that was. No, I mean this one over there. This also is a very good one, but it is.
Drop on you.
Yeah, but you know, you have noticed that it is soft. But it is the oldest one, the first one that I made, and they had to be made by hand, and it is about 15 years old, so it doesn't. I can't pump it again. I can't inflate it again. But these, they have to inflate to about 0.8 atmosphere. Well.
Well, I assume that you can define the roundness with less numbers for polygons. Okay? In this case, what would be the shape of the polygon with the least roundness? Not the maximum. The maximum probably is somewhat a circle. But what would look like polygon with the least roundness? If you can reply for a polyhedra with the least roundness, it is okay also for me.
Maybe the tetrahedron is one? It is quite, you know, the difference of the inscribed sphere and the circumscribed sphere of the tetrahedron is about 300%. Great difference of inscribed and circumscribed sphere. I think that is the worst one. Maybe that you know, and even another one. But, when you use it as a start for the subdivision of spheres, you get great distortions actually, as I have shown.
Yes, thank you very much for this interesting lecture. We will, sorry, but you can take it. We will have a